Okay, so we're picking up on chapter 16, finishing our discussion on how the sun creates energy, how it stays hot, and continues to pump out light into space. We were talking about the actual process, the nuclear process that does that in our sun, which well, you could say the type of star that our sun is. The process is called the proton-proton chain. Chains just like kind of stands in for process and refers to the fact that it's a chain reaction. So you could just as easily say proton-proton chain process or proton-proton process, right? We had been just talking about electron-proton annihilation, which was as you can see here in the title, step 1.5-ish, right? Kind of what does that mean? As I described before, it means it's a side step. So it's not part of the actual beginning to end of hydrogen to helium, but it produces energy. All the mass of the positron, which was created in step one, and an electron that the positron collides with and is attracted to, of course, right? So it doesn't, not only do they have to bump into each other, but they want to bump into each other because of their, opposing charges. And once they do, they both cease to exist and a gamma ray is produced. So all of their mass is converted to energy. All right, so let's quickly, I mentioned numbers and you got numbers in the homework, but we can just quickly summarize a couple things here. So if we look at these two particles, they both have the same mass. All right, so they both have the same mass. And that mass is 9.11 times 10 to the negative 31, or I guess it's 9.11, yeah, or 8.99. Somewhere around 9. We'll just round it to 9. So 9 times 10 to the negative 31 kilograms. So that's what we'll put right there. And this is going to be all about rounding. So it's fine. The number escapes me at the moment, the exact decimal value. So 9 times 10 to the negative 31 kilograms. One of the smallest masses that is, really firmly known, and that's again mass of the electron, which has to be the same as the mass of the positron. The only thing they differ in is their charge. It's God, when I started teaching just 10 years ago, it really was like the smallest, like really well-established mass. But as I mentioned in passing, in the last 5 years, there have been multiple like studies and a real consensus for a known mass of the neutrino as well. And so that's kind of really replaced in the textbooks and in example problems, the smallest known mass out there. So it's kind of interesting to see that shift, that continual progress of science. And within your lifetime, within your career, it just continues to happen. And then the only other value that we need to consider, and part of the reason I want to do this real fast is because it really does move quickly, and it's because using Einstein's equation, E equals mc squared, is truly straightforward because it's such a simple equation. It has just those three variables. There's no logarithms, no difficult algebra. The only thing is that, one quantity is squared, but overall, it just really couldn't be easier. So this is our mass of each particle. So we'll of course double it when we consider what happens. This is just the speed of light rounded to, I guess, if I had three sig figs like this, technically it should be 2.99. So, I'll just go ahead and erase one of them. But this is our approximate values here. And let's write our E equals mc squared equation because that's going to tell us how much energy the gamma rays have. And again, there has to be two because momentum has to be conserved, but essentially we're just finding all the energy that's being converted to light. When these two particles smash together, all the mass goes away. We have some really bright light. So we're just going to use E equals mc squared. Okay, now the m in this case is the total mass, so it's going to be twice the individual m. And I'll make that more clear by making this an uppercase M, just so you know it's not literally the same M. And then we would simply plug in. So if we want to find how much energy is produced due to this annihilation, I'd plug in the 2. So I'm going to have 2 times the 9. Well, let's round 9 to 10. So if I have 10 times 10 to the negative 31, that's the same as just 10 times 10 to the negative 30, right? Because it's, that, or rather, it's 10 to the negative 30. So if I, in other words, I round that 9 to a 10, and then I take it over to the exponent, therefore making this one bigger than it is. So it becomes negative 30 instead of negative 31. So I'd have 2 and then times 10 to the negative 30. So negative 30 right there. Okay, so that's the total mass. And then I got the speed of light squared. So 3 squared is 9. So that's, we'll approximate that as 10. Okay, so I'm just imagining squaring the whole C. Just square the coefficient first. That's the way you can deal with scientific notation always, because any power or exponent, or whatever you want to call it, distributes over multiplication. So I just square the coefficient, which is 9, rounded to 10, and then I have to square this term. And when you square something that is already a power, then you use the law of exponents, where raising is one power to another is the same as multiplication within the power or within the exponent. So then it becomes 16 is as the value that 10 is raised to. And that's simply because it's 10 raised to the 8 squared. So it would be 10 times 10 to the 16, approximately. All right. So then we take a look at this and we say, okay, well, then that's going to become 10 to the 17 once we combine our tens. So then we've got 10 to the negative 30 and 10 to the 17. What's the difference? It's negative 13. So we have 2 times 10 to the negative 13 joules. Okay, so you might think, well, that's not a very big number, 10, 2 times 10 to the negative 13, but it actually is a really big number, because when we start thinking about the, I mean, you only need 1 trillion electrons to get 1 joule, right? If you a little bit more, you need 10 trillion electrons, because a trillion, of course, is 10 to the 12. 1 trillion electrons is not that many. I mean, wires have, if you have like one centimeter of wire, you're going to have something like 1 billion trillion electrons in just 1 centimeter of wire that's carrying a current. And so, okay, well, right there, if you were to, annihilate that many electrons, you'd be getting 1 billion joules out of just the free electrons in 1 centimeter of like copper wire. So, so it just goes to show how much energy is contained in matter when you just convert it to light. Okay, so finally, moving on to step 2. In step 2, we go back to the main chain, all right? And now we're looking at the product of step 1, which is deuterium. Remember, that's an isotope of hydrogen. And what happens is the deuterium is now going to combine with a just standard hydrogen, a hydrogen 1, otherwise known as a proton. So we've got the product of step 1 combining with another of the available population of hydrogen. Because remember, these are the two things that started the chain in the first place. So we can see why proton is mentioned twice, proton, proton, because it's all about protons coming together. And this is obviously the most abundant element in the universe, most abundant element inside the core as well. The product of this fusion is an isotope of helium. So now we do have helium, but not the stable version of helium that we want. And that's important, because if this was the final product, it wouldn't really work, because there'd be nothing left over. The helium would just decay back down. That decaying process would mean that it there never would be a buildup of helium, and you wouldn't have this energetically favorable environment, because you'd be kind of like running out of energy if it just everything that was being produced was just breaking back into smaller pieces. Okay, so helium 3 is just an intermediate step, not something you're going to see every day, because it does have such a short half-life. When we talked about half-lives, we talked about these samples that people use to date things, half-lives also apply to these really small products and constituents of fusion because it's just anything that's unstable can have a half-life. So these unstable isotopes absolutely do, and they're usually fractions of a second. I don't remember what helium-3 is. Notice there is also that gamma ray produced. We talked about that before. As far as going, what's the story with the gamma rays? Because ultimately the sun makes light, so it makes sense to kind of go back and ground our understanding with what's going on with the light. Well, the gamma rays, right? Because they were produced in that side step. Now they're being produced in the main sequence in step two. They collide with particles on their way out of the sun. So as soon as they're produced, they're they don't get annihilated or anything, and they're not going to go back and create more matter, although it is possible. I won't go off on a tangent, but it's absolutely possible to create matter from pure light. There's something called pair production, for example, where you actually produce an electron and the positron. But that doesn't really happen in the conditions of stars. It can happen in laboratories, and there might be some natural occurrences of it that I don't know of. Don't know off the top of my head. But point being is that we shouldn't expect anything like that. The gamma rays will not turn back into matter. They're just going to stay as light. And anyway, they're going to get converted, however, to lower energy photons. So that, in other words, they don't stay as gamma rays. They will initially become X-rays and then ultraviolet and then eventually visible light. Some even becoming infrared. All right, so then the light we see, of course, is predominantly the light of the photosphere, light that corresponds to a black body radiation and is in the visible range, obviously much less energy than a gamma ray. So there's some sort of cascade of energy per photon that happens as the light makes its way out. We'll come back to that idea in just a minute. But let's, for now, finish up the proton-proton chain. All right, we've got to wrap it up so we can really kind of look at the big picture. And the last step of the fusion that occurs in our sun is actually called helium-4 fusion, and it's the production of helium-4. So what happens is you have the product of step two, which is
Excuse me, is there a quiz today?
the helium isotope. No. And then you have the other, basically from a side-by-side, occurring uh, concurrently, right? Yeah, so occurring concurrently, you have another isotope of helium produced. And you'll see in just a second when we zoom back out, that it's like two side-by-side tracks of these steps. So somewhere, right, from another step two, another isotope of helium was created, another helium-3. Okay, and that's again what helium-3 looks like. It's got the two protons, but only one neutron. And when they smash together, well, what happens? Well, you have the same sort of conservation that we talked about, conservation of charge and everything. It hasn't actually been as big of an issue. In other words, charge was naturally conserved here because we had two positive, charges coming in and two positive charges coming out. So we didn't need to worry about something like a positron being created. And same thing here. We have 4 as our net charge coming in, because remember the neutrons don't contribute, and we have 4 as our net charge coming out. But there's a byproduct in this case, and the byproduct of this final stage are more protons, more hydrogen 1, which is excellent for this being the type of self-sustaining reaction that nature likes, right? The kind of like, what type of reactions do you see in nature? Well, the kind that are most likely to sustain themselves, that are most likely to work in the first place. And this is that exact type, because there are other possible ways that this could have come about. But scientists considered all the options and realized that this was by far and has been confirmed with experimentation, observation, the way that the fusion happens inside of the sun. And what I'm talking about, just to hopefully clarify, is that these are just going to continue then the whole process because they can be used to start it all over again. Because what were the original inputs? Hydrogen, right? Hydrogen 1, just individual protons. Well, you've got 2 more of them being created with the final step. So, just kind of keeps everything going. It's not a runaway reaction. If you've ever we won't cover these, but if you ever looked at fission, When fission is described in like a compact solid, and you kind of you go through the similar process of like uranium fission, well, when you get to the last step, you have way more of the neutrons, which are kind of the stimulating bullets that will break apart the next atom, well, than you started with. And so that means at the end of each step, you see that all of a sudden things are just scaling up. And that's what's called a runaway reaction. That's how you can have fission make an explosion because it just it's just exponential growth with no sustainability. Whereas this fusion is sustainable. All right. So that's kind of the difference in runaway reaction versus a sustainable one. Really fascinating ideas that we don't have the time or the scope to get into. But anyway, the final thing, right? The main point of all this fusion is this right here. This is what's being made by the sun. Not that, okay, like that's the purpose of the sun is to make helium. Far from it. It's really kind of just going to build up inside the sun. It's not itself being fused and won't be until the later life stages of the sun. But it still is, as I said, stable. And so it's the end of the line. Once it's made, nothing's going to happen with it. And it's just going to sort of like sink down inside the core and just rest there until eventually the core contracts and becomes hot enough to actually start fusing the helium into something else. But it is definitely the final product of the fusion inside the sun. Okay, so and then as I said, the leftover protons go on to other proton chains. The helium just sticks around as a inert, final product. And I thought it showed it again, so I wanted to get a zoom to show you one more time because it didn't have it here. So here, this one doesn't have labels, but this is the whole picture that we just finished talking about, all the way from step one, side step over here, 1.5, right where I showed you the numbers, step two, and finally step three. And then, and I said there was the two concurrent tracks that merge for the final step three. Well, that I was talking about right here, and then this being the merger, because this is step three. All right. So does that all make sense? Is there anything that is you want like felt like strictly confusing? Because it'd be a good chance to ask if you are wondering. I want it to make sense. Um, I get that it might not make perfect sense, but it will come up quite a bit. So, any questions? Okay. Well, thank you, Maxwell. Um, I'm glad I did. Okay. Well, let's move right on to the solar interior. Okay. So now that we've established where the energy comes from, where the heat comes from, let's talk more about the structure and the balance inside of the sun. So, what do we know about the state of matter inside the sun? What is it? Solid, liquid, gas, plasma, Bose-Einstein condensate? Okay, I got two people put down three as their answer. Thank you. Excuse me. Need more coffee. Okay. Anyone else want to venture a vote, a guess, an answer? Okay. Thank you,
Did
Elizabeth.
I say plasma?
That was Kylie, right?
Yes.
Yep. Thank you. Like unless I have the video thing up, it's hard to tell, but I recognize your voice. Cool. Yeah. Yeah. I thought it might be too easy because I felt like I had, kept saying that over and over again, but it makes me feel better about repeating myself. At least within reason. So it's a plasma. So the state of matter in the sun is a plasma. And so real fast, what is a plasma? It's just another state of matter. It's by far most similar to a gas. So, you got your rules that define the different states of matter. Uh, just to, quickly summarize them, a solid has both a defined shape and a defined volume. A liquid has a defined volume, but not a defined shape. So liquids can't expand or contract freely. They're basically incompressible, and but they do not hold their shape, right? They flow. A gas has neither a defined shape nor a defined volume. It will fill whatever space you give it. Obviously doesn't, have a particular form to it, doesn't stay as a rectangle, right? Because it just flows as well. And it can, change its density easily, whereas a liquid cannot. So the gas can be easily, expanded or compressed. So with those three definitions, it kind of like summarizes, like a whole idea, right? Because it was with all three of these states of matter, solid, liquid, gas, the only thing we considered was, do you hold your shape and do you hold your volume? And we literally, had yes, 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 no, and no, no. So that's it, right? And in a sense, it is because that, like if that's the only way we're thinking about matter, then solid, liquid, gas is all we need. What the only reason that plasma is, accurately described as, as far as any classification can be, as a fourth state of matter is because it, it does behave fundamentally differently, but obviously it doesn't relate to those two questions. Does it retain its shape and does it retain its volume? There's got to be another question, right? And in this case, the only question is that is it charged? Right? Which never came up before, right? We didn't care if the solid, had charge or the liquid had charge, right? But it turns out that with the plasma, that is the defining difference, is that plasma is a charged gas. So instead of it being neutral, it now has charge. The way that if you remember a phrase that I kept saying, is it's an ionized gas because it's lost its electrons. Yeah. Oh, no worries, Maxwell. So yeah, maybe you're like, oh yeah, I knew it was plasma, but yeah, just didn't register. So that's the whole sun is that ionized gas. So charged gas or ionized gas mean the same thing. The last thing I'll say on this, because I'm probably already spending a lot of time on it, is that although the questions that I led with are the standard way and a good way of thinking about solid liquid gas, right? Does it hold shape? Does it hold its volume? Really, really helpful, concept. The way that we can seamlessly include plasma is to just say that all of these states of matter don't necessarily have to do with those two questions about shape and volume, but instead just have to do with how energized they are. And so if I just put E here to represent, the energy that you put into the matter, then you start with a solid, you put in more energy, it melts and becomes a liquid. You put in even more energy, it vaporizes and becomes a gas. Okay, that all makes sense. We've heard about that. The phase changes, as they're called, because these are phases of matter. You put in even more energy, the gas becomes a plasma. So in that regard, there actually is a real clear through line, a conceptual connection to go right from solid to plasma. So we can't see the sun's interior directly, so we rely on models that best fit our available evidence. The models assume that the sun is a plasma, so that is important for the physical models that scientists use. They get rather complex, as you would guess, but they definitely need to know that it's a charged gas because those behave differently than neutral ones. It's stable. What does that mean? Okay, because I talked about the magnetic field being kind of chaotic, but then again, we saw it goes through cycles, so it's chaotic, but in a predictable way. And what stable means here is that there's no long-term large-scale changes. So the sun right now and for a long time to come is just going to stay the way it is. So any fluctuations are going to be self-regulated. The sun is just going to, always maintain the same size, the same density, the same temperature. So that's the idea. And that stability is kind of reflected here or repeated with not cooling down. So this would be like a energy balance, okay? And then stable you think could just be a volume balance or a mass balance, however you want to put it. We talked about, I said before, right, that all that mass that is just disappearing, literally becoming light, is just so small that it actually just doesn't show up in the large scale changes. It's just totally insignificant, and which is so interesting because you can't deny it's there, right? It's like it is a gradual loss in mass. But in the same way that you could say, okay, well, there's a if you're losing like, one bacteria from your, all the like, the bacteria that live inside your body, you're losing one of those a day. Well, you could lose one a day for your whole life, and it wouldn't make any significant difference. Your life would be look identical to the best physician or medical researcher. They couldn't tell because it would just be an insignificant loss. Well, similarly for the sun, because it's so big. Okay, so if we're talking about stability, so definitely two and related to three, gravity attempts to do what? Okay, so probably know this, but just want to make sure. Just going back to the basics here, talking about the sun. The sun, after all, was created by a big cloud that collapsed. The leftovers formed all the planets, remember? So, what about the effect, the continued effect? So, thumbs up, thumbs down, or one for contract, two for expand. I assume the one for Maxwell is contract. Okay, yep. All right. So, as you can tell from my enthusiastic yep, thank you, Kylie, that it is indeed contract. That's what gravity does. Okay. Gravity is just a one-trick pony. It can only do one thing. It just pulls things together and tries to squish them. And that's what it's doing with the sun. So it just wants to contract the sun. All right. So these green arrows would represent the gravitational influence on some level of the sun. So like imagine the dashed circle just being some interior level because that's where our focus is right now. Okay. If you want to talk about the surface of the sun, go back to chapter 15. And so, we're looking inside. This would probably be like, kind of somewhere, in the lower convection layer, maybe, right kind of where the radiation level meets the convection level. Well, regardless, gravity is pushing inwards, but the sun stays the same size. So what pushes back? All right. Well, the outward pressure that balances gravity's desire to contract is the pressure that comes from the hot gas. Because when you heat things up, they want to expand. That's a force, right? Pressure is just force over area. So it's very easy to relate forces and pressures. It just happens seamlessly, naturally, often done. So that's what's happening here. Whether these arrows are a pressure arrow or a force arrow, it doesn't matter. They serve the same purpose. But what they show us is that there's a balance. The pressure pushing back against gravity is the same as gravity trying to contract. And so they're at a stalemate. So there's neither expansion nor contraction. But that's because of all that heat that's being produced. And all that heat we know comes from this remarkable physical process called fusion. It couldn't come from anywhere else. No other heat process could withstand gravity like fusion does. This type of phenomenon where you have a balance is a hydrostatic equilibrium. Hydrostatic, not because it's water, but because it has fluid properties. And if you might notice that fluid is a word that almost like just that like it I do this, I don't know if everyone else does, that when I hear fluid, I almost like hear the word liquid because it just like sound like synonyms. But a fluid is not, it wasn't liquid, right? It didn't show up as one of those phases. Fluid is actually a term that applies to liquids, gases, and plasmas because they all flow. Fun fact. But hydrostatic is just that, right? So it's not a solid. So it's able to deform and flow, but it's in equilibrium because of those balances. Balanced pressure in with pressure out. So does it just stay like totally balanced all the time? Of course not, right? There's going to always be things that cause perturbations. Perturbation is a term that astronomers love. It just means some small disruption, some small change, a perturbation. And what happens, right? So small changes inside the sun, as well, they are self-correcting because that's otherwise the sun wouldn't be stable. So the sun is in a equilibrium, and the type is a stable equilibrium. So stable equilibriums are like if you hold something and you have, I want to show you something real fast. So if you look at the video picture of me, so if you have a pin and you act like it's like a pendulum and you hang it this way where it's fixed to my fingers and I give it a little push to the side, it will swing back to where it started because that is a self-correcting equilibrium. But if I try to balance it on the top of my finger so that it's straight upwards, I can, right? If and maybe if it was a slightly larger object, or I can for a split second. But as soon as it starts to fall, as soon as it starts to tip, there's it just continues to tip, and it just picks up speed, and then it just completely, falls over. So although that when it's balanced straight up is an equilibrium because it is balanced, well, the fact that it can't stay balanced easily shows that it's an unstable equilibrium. Well, the sun is a stable one. So the sun is like the pendulum that wants to correct itself. It'll just easily swing back to where it started. But the swings here are, not literal, but, is just an analogy because the swings here are this like, processes of energy and but the idea is the same. All right. So let's see if that makes sense to you all. And if you can kind of interpret how it's represented in this figure and with these options in the table. So if the sun contracts a bit, because that just happens naturally for some reason, right? Some influence from a planet or, another passing star or where we are relative to the galactic center. There's all these reasons. What happens to the sun's interior pressure and temperature? Okay, so if the sun contracts a bit, for whatever reason, what happens? Think about your answer and throw it in chat. Okay, I've got one answer so far. Thank you, Maxwell. Thank you, Elizabeth. Anybody else? All right, Maria, excellent. Okay, let's see. This one is one that doesn't show you. Okay. There's a few that are missing it. I have to go back and like circle it, but not this time. So as we can see, yep, hey, yeah, you corrected yourself. That's even better as an educational, process. So the temperature and pressure both go up. So the correct answer is one. So it and almost like in the other order. So it's like because it contracts, well, that causes the pressure to increase. If the pressure increases, so does the temperature. It kind of makes sense. You squish something, there's nowhere else for the energy to go. There's a number of ways we could say, why the temperature goes up. There's a whole, way of thinking about that in terms of the laws of thermodynamics, the whole thing I teach when I teach physics. But separately but totally related, we could say it's all about fusion rates. It's just like because you have more chance of the collisions of those protons that start the whole fusion process. So however you want to think about it, when you make things smaller and tighter, pressure goes up and so does temperature. I think and hopefully fairly intuitive as long as you have like confidence that it's the way to go. So that that figure showing it, right? So the arrows look unbalanced because for some amount of time they are. And if this like sounds vaguely familiar to something we talked about, I hope it does because it is similar to when we talked about the greenhouse effect, right? And how planets are in equilibrium. You know how they get disrupted but then return. So like any disruption, takes some time to account, to account for, to accommodate, but eventually it is accommodated. Same thing here. The time delay, it could vary. I don't know. For the sun, who knows how long? Days, hours, years, but hundreds of years, thousands of years. But whatever it is, it will return to a balance. And so if the green arrow gets bigger because, you know, everything got smaller and therefore gravity got stronger, right? Because if you take the same amount of mass and you make it smaller, well, that causes gravity to go up. Just remember the universal law. So, well, then eventually the pressure is going to accommodate and balance out that greater influence from gravity. This is just making sure we understand that pressure varies with depth. So all of these balances that we talk about are going to apply to any different depth of the sun. So in other words, any one of these dashed circles, no matter where we draw it, whether we're talking about an equilibrium happening in the core or some other level of the sun, it's always going to be equilibrium. Always a balance between outward heat pressure and inward gravity, but the number that is being balanced changes with depth. So, we know that from like swimming, right? So when you go down into a fluid, the pressure increases with depth. So that happens, when there's still an equilibrium, but it just naturally happens. And it's just called, like depth dependent pressure. Okay. Oh, and thank you for the answer. I was just gonna move right on, but you're totally always welcome to answer them, and I encourage it. Even the times I don't read it, like I say, sometimes I'm like, throw it in chat. I don't have a chance to look at it right now, but come back to it. So the weight of the water above you pushing down increases pressure. So it totally makes sense that the deeper you go, more weight above you, more pressure. Okay, applies to going down in solid rock too, except there the rock is holding the pressure rather than you, so you don't feel it in the same way that you do when you're swimming in a fluid. So just to make sure that that idea makes sense for the sun and all the equilibriums that we've been talking about, we've got pressure inside the sun, and we're asked of the two options, which best illustrates the gravity and pressure of layers at different depths. So they're asking for, so they, do these two figures best represent equilibrium at two different depths, and the different depths are the different dashed circles, or does this figure over here and these pair of figures represent the way that gravity and pressure remain balanced at different depths? So which one? Thumbs up or thumbs down? Mhm. So we got one vote for up. Elizabeth says down. Maria says down. Jason says down. Okay. 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 All right. So many of you had it correct. Thumbs down. Option two. How do we know? Well, because the pressure increases closer to the center of the sun. Like just think gravity, right? Gravity increases the closer we get in. So that means that the balance, since it has to be maintained everywhere, has to change as well. So then the outward pressure increases with depth as well. So here, since the depth is small, the two arrows that are balancing, the inward and outward arrows, are themselves each small. But at a greater depth, closer to the center, well, the two arrows are each bigger, but still equal in size. So that's the idea. Yeah, cool. Yeah, yeah. Cool, cool, cool. Hope they all make sense. Good things to, yeah, just to clarify, ground our understanding. So we'll just kind of wrap this up about this idea of the balance. So we're keeping the interior balanced, the temperature and pressure increase closer to the center of the sun, right? But that balance is always maintained. We saw these graphs back in this figure slash graph back in chapter 15, just showing the temperature on the vertical axis as a function of distance from the center, measured in kilometers, with the 0 being the very center, the core extending to this value right here, which looks to be maybe like 160. It's a linear scale. So maybe 200 and 190, I don't know, 1,000 kilometers. And then, we got the different zones, different distances, all the way up to 700,000, which is, if you remember, the radius of the sun. So that means since it started at zero, which is the core, hitting 700,000 is going one radii away from the center, which means you hit the surface. So that's that this right here, this edge is the photosphere. And the bottom graph is all the same information on the horizontal, but has density in grams per cubic centimeter as our vertical axis. And so we got some reference densities shown for the different regions of the sun, gold, water, air, and the temperature scale just has our numbers in Kelvin, by the way. All right, so lots of good information here, good summary. We know the solar energy source, of course, is fusion. All right, so the energy lost as light is replaced by fusion. Okay, so what are we talking about here? We're talking about the energy balance rather than the size balance. But don't get me wrong, the two are definitely related. It's kind of like two sides of the same coin. But it does still make sense to focus on one or the other. So, right, so we produce a certain amount of energy with fusion. That can't be more than the energy that is moving away from the sun as light. Yeah, are there other ways that energy moves away from the sun? Well, the solar flares would carry a certain amount of energy. The solar wind is a steady flow of energy, but it ends up being just really small compared to the amount of energy that leaves as light. So even though the solar wind is, kind of a big deal for those solar storms we talked about and creates beautiful auroras, in terms of just sheer numerical energy, the joules that the solar wind carries away is like 1% of the total energy that the sun produces. It's quite small. So I had a problem in previous years, like 5 years ago. I had a homework problem where we actually, compared the values, but I haven't assigned that one for a while. So the actual number is not at the front of my mind. So sorry for not knowing it. Anyway, you can, do a deep dive in Wikipedia and learn all about how much energy the solar wind carries. Anyway, check your understanding. Photons from the sun. So a high energy photon, remember that's a particle of light, is produced by a nuclear reaction at the center of the sun. This energy will leave the sun soon after as a high energy photon, soon after as a bunch of low energy photons, much later as a high energy photon, or much later as a bunch of lower energy photons. So do you necessarily already know this? Not, I haven't spelled it out. So this isn't just like a check if you're paying attention question. You got to kind of like connect ideas. And it's also going to be a segue of things we're about to talk about in the next slide. Okay, so I'm going to not check chat or anything, but it's just to show you the answer. But if you want to kind of, see if you're right, then take a moment. And it is 4. So much later, so there's a real big delay between those gamma rays that are produced and the light that actually leaves the surface of the sun. And the light that leaves the surface, I did say this, but among many other things, is low energy photons. Because, of course, the surface has visible light photons, which are much less energy than gamma rays. Okay, because the energy had to go all the way from gamma to X-ray to ultraviolet and finally to visible. So it's a big swath of the electromagnetic spectrum. Furthermore, a photon is created in the core by nuclear fusion as, well, this one we definitely know, right? If you're paying attention, literally just said it, gamma ray. Okay? So this is the only type of light that is produced inside the core. Just think of that, it's so hot. Remember, it's over 10 million Kelvin. And so that, and the fusion process itself being such a high energy process, of course, it can only occur at that high temperature. Well, then the only type of light that's around are gamma rays. Okay, no other lower energy light exists inside the core. All right, so there's the one from annihilation, and here's the gamma ray produced in step 2 of the of the PP chain, proton-proton chain, because those are the 2 points. Okay, it not like a deal breaker if you don't remember exactly what happens and exactly what step. You can always reference it, right? Everything's open note. But if you care to remember, if it kind of helps you, just remember that gamma rays are only produced in the side step and step 2. So a photon is created in the core by nuclear fusion as a gamma ray. Moving away from the core, the atoms enter the blank zone layer, okay? So kind of like me, they can't decide whether they want to call it a zone or a layer or a level for that matter, where the most important method for heat transfer is blank. And notice there's two blanks, but each time only one word. So whatever this zone is called, it has to be the same as the method of heat transfer. So what is it? The atoms enter the, here I'll check. So I'll look at the time to make sure I get, so who has the answer to this one? What's the name of the zone that is also the name of the mechanism of heat transfer? Okay. And Maxwell, that answer that just came in, that's for this one? Yeah. Okay. Okay. Got another one from Maria. I always look at like the time it comes in to see if it's like a previous answer to the current one. Yeah, okay. So Kaylee says, okay. So I've got 2 votes for convection, 3 votes for convection. All right, Kylie and Kaylee and Maria. Okay. Elizabeth as well. Okay. Well, you're going to be disappointed. It's radiation. So, because it said moving away from the core. So, what happens first? Convection happens, but not first. Okay. So, there was one that showed it here. So, we've seen this figure before, but it's right here, the radiative zone. I guess to be fair, right? Sometimes it's called the radiative zone, but you can also call it the radiation zone. So, it's sort of like, do you use the adjective or not? It works either way. Maybe an English teacher would give you a hard time. Okay. Yep. Yeah. So that's the first place after the core. The first place that energy goes when it leaves the core, and the core is the only place where fusion happens. Okay, so all the fusions in the core, all those gamma rays are produced. The gamma rays are going to carry the energy that the sun, then delivers to the rest of the solar system. Where do those gamma rays go when they leave the core? They go to the radiation zone before going anywhere else. All right. Well, I'm glad we talked about it so that you can clarify. Okay. So through the radiation zone. All right. If you looked at the next slide, I bet you would have, you know, been having the answer given away. In the radiation zone, most atoms are still ions. Okay, so it's still a form of plasma. So the photons are rarely absorbed. So we say the layer is transparent. Transparent in the way that a gas can be transparent, which is slightly different than the way like solids are transparent. But regardless, what does that look like? The fact that most of the atoms are still ions and the photons can't be absorbed. Okay, so it means that the energy is going to stay as light. So, in other words, the energy of those gamma rays can't turn into quote unquote heat yet, and which is a little bit of a misnomer. And I don't mean to like confuse matters, but that's the way we would normally say it. Um, okay, how much do I want to kind of get into this? But okay, so what I mean is that heat is like messy energy, right? It's like, hot air, boiling water, magma in the surface of the earth. It's the convection zone once you get higher up in the sun and closer to the surface, because there you have big, convection cells of hot plasma, moving in big circles. Okay, so what's happened there is absorption, because absorption means that the light energy has been given to some particle, some molecule, some individual atom, and caused it to bounce around and then, bounce into its neighbors and cause a bunch of random commotion and motion that we think of as hot substances. Okay, because that's the hot things have faster moving, molecules and faster moving atoms. So without absorption, you don't that whole idea of the material heating up doesn't happen. So the radiation zone doesn't get any hotter than it already is because it it doesn't have a way to. It can't absorb the heat. The heat just has to pass through it, which is kind of this strange idea. And you remember I kind of described it as like this like huge sheet of glass. And glass actually kind of does, as a transparent solid, at least follow this idea, doesn't tend to heat up that much, right? Because it just lets the light through. Glass does absorb some infrared, and it will get warm to the touch. But since it's not absorbing visible or ultraviolet light, it's just letting that higher energy light through. It stays much cooler than things on either side of it. So glass will stay cool because it's transparent. Well, the radiation zone kind of works that way too. But that's not the main idea. The main idea is the path of the photons. So let's get back to it. Okay, but I still want you to kind of like understand the justification for a sentence like this. So photon comes in, right, to this area where it can't get absorbed. So in other words, these, atoms, right, because this is, your helium-3, and, here you got your hydrogen-1. Here you have hydrogen-2. So you got a deuterium, a hydrogen, and a helium-3. So with them, no absorption. So the photon can't just deliver its energy to that atom. And there's a whole reason why. It's Remember how we talked about energy levels, right? And emission and absorption spectra. Well, those are excitation levels of electrons. But if you don't have electrons in your orbit, there's you can't excite them. So there's no way to excite these nuclei. There is such a thing as an excited nucleus, but it doesn't match the energy of the photons. So, because it's actually the really high energy states. So almost none of this energy can possibly get absorbed. All it can do is ricochet around. It literally can bounce off, and the collisions follow just traditional physics collisions. The understanding how these collisions work is no different than understanding the way that billiard balls smash into each other. It's literally the same equations. Like obviously there's many more of them, and so you can't really follow, every photon, but it truly is the same idea. So you have this photon that is just bouncing around, not able to deliver its energy, and just trying to go somewhere, right? Just kind of taking what's called this random path, all right? The scattering off of nuclei, like pinballs bouncing off of obstacles. All right, so the long random walk, and the random walk is kind of the term that's given to it because it's, the chance of it bouncing in any one direction is randomly chosen, um, causes these photons to really take their time as they move through the radiation zone. And this figure almost like shows it going all the way up to the convection zone. Don't worry about it. I don't know if it's supposed to represent the whole sun or not. But regardless, there's this long random walk for the photon because it can't do anything else. It can't deliver its energy. It's just, trapped there as a photon. So when we talked about eventually that, the gamma ray becoming something else, that doesn't really happen until the very upper level of the radiation zone or the convection zone itself, where it's finally able to become lower energy light. Okay, I want to kind of move a little bit quicker for this next material, although we're taking a break probably before we finish. But moving all the way up to the surface, we've got these granules. The reason we're mentioning them is because we're gonna make sure we for fairness' sake mention another version of heat transfer because we're talking a bunch about radiation and all these interesting ideas. But convection, of course, occurs. There literally is a region called the convection zone, and that happens at the upper layers of the sun and is what we see at the surface with those granules because they're all part of those convection cells, the hot gas rising before it sinks and cools. And remember how that relates to sunspots. Well, I won't review it now, but do remember that there's an important connection to convection and the magnetic field of the sun and sunspots. Okay, so about the convection zone, just more about the energy. In the convection zone, photons are absorbed, okay, and heat the gas. So this is like more what you would expect, okay, because it's like more everyday, not totally exotic physics, because it's more it's still super hot, but not so hot that it's ionized. So now we have a rising to the surface of that heated up gas. Okay, so here are the incoming gamma rays that made their way through the radiation zone. Okay, so once okay, so let's just point out in the convection zone, the molecules, the atoms really, are cool enough for some atoms to form. And they become atoms instead of ions once they're able to hold on to an electron. So now that's why they can absorb. So you see there's a whole kind of cause and effect here. You're too hot, you don't have any electrons, so you're not an atom, you're an ion. Okay? That means you can't absorb energy. Once you cool down, you now can hold on to your electron. You become an atom instead of an ion, and now you can absorb light energy. So absorption slows down the photons, which traps heat in the gas. Hot gas rises towards the surface. So there's your convection. Now, finally, in the photosphere, I always want to get to this stage. We get to space essentially, right? The density of the atoms is very low. So we get to a point where photons are now emitted from the hot gas and can escape into space. Because the photosphere is a sudden drop off in density. It's a boundary of the sun, right? Of course, we know that there's an atmosphere and a corona that extends way out, but those are all really low density. So there's a drastic kind of final, surface-like edge of the sun where the density, almost drops off to the quote unquote vacuum of space. They say quote unquote because space is never a true vacuum, it just gets really low. And that means that the only way for heat to move through such a low density environment, the near vacuum of space, is to go back to radiation. All right, so they're going to they're going to escape into space. They're emitted from the hot gas, right? And then they go out, so spread apart from atoms on a photoscope if you want to see them. So they radiate into space. So when you say light escaping into space, that's back to what mechanism of heat flow? Radiation. Again, literally, it's radiation under very different conditions because we don't have to worry about the whole, pinball idea, but it is literally the same mechanism. So you had radiation in the radiation zone right outside the core. Once you get into space, you go back to radiation. The only mechanism of heat transfer in between is convection. Okay, so let's take our break. Okay, so to finish off chapter 16, we'll look at the last section, excuse me, called Peering into the Sun. This is just going to quickly summarize the way that scientists, the way that astronomers are able to investigate the sun. All right, so one way is they use something with a cool name called helioseismology. So seismology, like the study of earthquakes, and helio, like the word for the sun. Like remember heliocentric solar system? So the helioseismology is the study of solar surface patterns. So you can think of them as waves, vibration patterns of a ringing bell, right? Because if this whole thing is, under so much energy and stress, then there's going to be all these interesting vibrations, resonances that form, and scientists are able to study. And they're kind of showing, these like waveforms on the 3D sphere of the sun in this figure. So, like seismic waves from earthquakes, internal layers change the way that the waves propagate. So we can learn about the interior from them. So we look for, events that are similar to earthquakes and try to study their influence on the sun at different points. I'm going to move through these questions quickly and not check for answers. The regions on the sun's surface that are redshifted must be moving. Okay, so why are we talking about redshifts if we're talking about seismology? Because, well, the only way we can measure vibrations is to look at the movement by, with a telescope in visual spectrum or not. And that, in other words, we can't put a sensor on the surface and actually measure a physical vibration. So we just have to look at things moving. What's the best way to tell if something is moving away from us or towards us? Red shifts and blue shifts. So if there's a red shift, that means that part of the surface is moving away from us or sinking into the sun. Okay, so any red shifted section of the surface is sinking or moving deeper into the sun. Redshift, moving away. right? And that indeed the red shifts and blue shifts are what are shown in the figure. So what we've learned from helioseismology and relating it to models that account for the sun's rotation, we've learned that the convection zone also experiences differential rotation. So it doesn't move as a solid. We've learned that the radiation zone and core rotate like a solid, all right, so that they don't rotate at different rates at different latitudes. We learned that the amount of hydrogen and helium is the same at the surface as inside the star, and it only changes in percentage or proportion once you reach the core. All right. Um, when helioseismology has helped in the understanding of sunspots with confirmation from direct measuring of magnetic fields. We've learned that the cool sinking gas under the sunspots act like a plug to block the hotter gas from rising. So we've gained a deeper understanding of how the actual fluid flow works. And we've learned that the sinking gas pulls in new gas and magnetic field from above it. All right, so lots of important discoveries. Okay, but helioseismology is not the star of the show. The star of the show is the neutrino, that weird little particle that we talked about back when we talked about the PP chain, step one. If you remember, it was the other byproduct along with the positron, but it never got mentioned again. Now it's back. So the neutrino, okay, tiny little particles that are produced in order to conserve angular momentum. They were hypothesized in the 1930s to explain the missing mass or energy and momentum, angular momentum in particular, from radioactive decay. This actually was the early days of understanding things like this, basically quantum mechanics. Okay, so here we have production of a neutrino. It's that little pink one there. Neutrinos were, from their very early days of being hypothesized, understood to not interact with matter very much. They were assumed to escape freely from the interior of the sun at nearly the speed of light, and that made them consequently very difficult to observe because they are very light. All right, so they have no significant gravity effects. We could almost say the same for electrons, so let alone for a neutrino that is about a millionth as massive, less than a millionth as massive as an electron. They're neutral, so no electric effects, and they move incredibly fast, so there's not much time to observe them. Again, they move nearly at the speed of light, something like 99.9% the speed of light. They are sometimes called ghost particles. Right? I had to say it like that. So neutrino detection is hard. That is a understatement. And it's kind of the typical dumb science humor, right? It's hard. It truly is. It's fascinating the journey that scientists have taken ever since the 1930s, right? All right, so here we have how hard it is. This is our neutrino, by the way. And this is just some atom because at the end of the day, if we're going to detect a neutrino, literally just to confirm that they really exist, we have to have it do something. In other words, it needs to hit this atom, and it doesn't want to. Neutrinos can just pass through things, and only under just the right conditions, which means and very unlikely because you can't, set up the conditions because you don't know where the neutrinos are coming from. But there's some small chance that if the neutrino comes in at just the right angle, it can hit a nucleon head on and actually cause a reaction. So when neutrinos collide with a nucleon, again, they have to literally hit it head on. They can change the nucleon's type. Okay? And notice that what they do, they don't cause, a major change. They just change the type of the nucleon. So changing which nucleon will change the type of atom there is. Okay, so if you change a proton to a neutron, will that change the type of atom, as in like the name on the periodic table? If you change a neutron to a proton, would that change the type of atom? Well, this is a trick question. Just tell you right away. It's both of them. It's thumbs up and thumbs down at the same time. Good thing we have two hands. All right. So that's the change that a neutrino can induce in the rare chance that it actually hits a nucleon of an atom head on. It'll cause a neutron to become a proton, or it'll cause a proton to become a neutron. So here we have it. So when neutrinos collide with a nucleon, and remember, nucleon is a term that is collective for both protons and neutrons. I know at this point we have a lot of similar sounding words: neutrino, neutron, nucleon. Get them all straight as best you can. Okay, so when that happens, when the collision happens, there is a change in the nucleon's type, as we said. Okay, for example, the change could be N to P. That'd be neutron to proton. Or it could be P to N, which is proton to neutron. So in other words, that atom could end up having one extra proton and become, one higher on the periodic table, or it could have one fewer proton and become one lower. So we know that the neutron was there by detecting the results of the change. So this is actually, I meant to fix this typo because you can tell it's supposed to say neutrino. So we know that the neutrino, neutrino, T-R-I-N-O, was there by detecting the results of the changed atom type. So that's our evidence of the neutrino collision. Okay. There's one other thing they can do. They can bounce off an electron. This is even less likely because they have to hit the radius of the electron, essentially, which is an even smaller target. And when they do so, they cause the emission of light due to electron excitation and immediate relaxing. So they cause, a little bit of a change here in the electron level, which causes the overall atom to emit light. So in this case, we know that the neutrino was there by detecting the light from the electrons. Okay, so we have this particle that's produced naturally in the fusion in the sun. It doesn't like to interact with anything. It can just race through matter, can pass through the whole Earth, and we don't even know. But sometimes, under very specific conditions, it can do one of these two things, okay? Change a nucleon or cause an electron in orbit to emit light. So, ever since they were first hypothesized, big research projects have gone into studying neutrinos, which came down to trying to actually essentially capture some, just measure some, right? Just literally just confirm they exist to begin with, and then make measurements about how many are coming, from the sun, and so on. Okay, so experiments of this sort, these neutrino detection experiments, require huge amounts of material because of that tiny chance of interaction. The only way to actually do this with any chance of success is to have huge volumes of interacting material that's monitored in some sophisticated way. So it always involves some sort of huge tank system. Look at the person for scale here. Okay, here's another huge tank system. Notice both of these are surrounded by rock. That's because they have to be built underground. Okay, they're built deep underground so nothing else will interact with them because they're these are miles underground. These are deep, deep mines. They're almost exclusively abandoned salt mines or decommissioned salt mines. And then these huge tanks and sophisticated operations are set up inside of them in some of the deepest chambers because they don't want anything else to be interacting with their tank other than neutrinos, and nothing else really makes its way that deep into rock except for some long wavelength radio waves, which they can easily account for. Okay, so really, the neutrinos are the only thing that it's going to be passing through, a couple miles of rock, because that's no big deal for a neutrino that can pass through the whole Earth without even slowing down. So, for example, this like one of the tanks had uh, 9 times 10 to the 30 chlorine atoms, or in other words, 100,000 gallons of chlorine that they were using as their material to monitor and look for those changes we talked about. And essentially, you're wondering like, wait, how would that work? They're just kind of held in some sort of like particular condition where they're able to carefully tell if there's a change. So, kind of think like, if you had it at just the right temperature, just the right pressure, and if there's, some disruption in the chlorine, and maybe the chlorine can like, there's like something about it can like easily be monitored. So they choose the molecule for particular reasons. To just go back to the numbers here and the thing about neutrinos, right, is that we have about 45 times 10 to the 10 of them per square inch every second. So there's a huge number of these neutrinos just passing through us, the planet, at any given second. Huge, huge number. Okay. But only one of them interacts per day. Okay. So, and this is so we have, this many per square inch every second on the whole Earth. And how many, and by when they say interaction, right? So this is a rough estimate. But on what like scale? The whole Earth. So this is a cool number that actually kind of is fairly accurate. That really, on average, one neutrino interaction in the entire volume of the planet Earth happens each day. So that means what's the chance of an interaction happening in this tank? Because the tank is, big by tank standards, but not by Earth standards. It's tiny. So they have to wait huge periods of time to get there to, actually have an interaction. So once the whole project is set up, it's not like the data just comes, flowing in. It's like, one measurement, per month at best. They were first finally confirmed in 1956. The number coming from the sun was counted in the 1960s. This actually led to a big, like, kind of moment in physics. One of the kind of famous events in the later half of the 20th century in terms of physics events, almost as like big a deal to particle physicists as like, relativity is to physics in general, which happened in the night, much earlier in the 1910s. All right, because only a third of the expected number were detected. This then led to a conclusion that was already on people's minds, but not widely accepted, that neutrinos actually oscillate. This is a whole interesting idea that's beyond the scope of the class mostly, but basically that they change. And this had huge, huge consequences, but didn't really help with our understanding of the sun in particular, other than that we needed to know this, that they oscillate. Otherwise, we would have been getting the wrong numbers from the sun. Okay. And then finally, solar neutrino oscillations. In the 1990s, confirmation that solar neutrinos are changing flavor. What's that? That's the name given to their different states. So I guess physicists needed another word for describing things, and they'd already used charge and whatever other expressions. So they started referring to particle flavor. It's the same with quarks. Quarks also have different flavors. Quarks, by the way, are the building blocks of protons and neutrons. And so this, so we have now, we're able to relate this idea about neutrinos back to the sun, and all this kind of came to a full circle. And now, there's still tons of unanswered questions, but we now have a much better understanding of neutrinos and therefore a much better understanding of the sun. Because what I don't want to lose sight of is that the reason that in this class and for a solar scientist, neutrinos are interesting is because of the very reason that they're difficult to detect. They pass right through things, which means a neutrino that's created in the core of the sun just goes right through the sun and heads straight to Earth. So you only have to wait however long it takes light to travel from the sun to Earth, which is about 7 minutes, to get a signal from the core, as long as you're able to actually get it, right? But the point is that there's no time delay. So when you do measure a neutrino, you're getting live data, so to speak, of what's going on inside the core. Whereas those photons that bounce around like, pinballs in the radiation zone, they take thousands of years to get up to the convection zone. And even then, like, what do they tell us directly about the core? Some things in terms of, run some calculations, but neutrinos tell us what's happening in the core at that instant. So quite remarkable. And by the way, these are the four Nobel Prizes that have been awarded in all Nobel Prizes in physics, not surprising, Not Nobel Peace Prizes, right? That nothing directly to do with peace. But four Nobel Prizes in physics, so physics Nobel Prizes, uh, for neutrinos research. So obviously it's been a big deal since there's only one of those a year, you know. All right, so there you go. Everything you need to know about the sun. Yeah, both. Exactly. I like that. I like what Maxwell put. No, there we go. Okay. Okay. Let's stop this one.